Hello everyone. Now we are going to discuss the type of loads that are acting on the beam. So we'll start directly with the first type of load, and it is point load. So it is basically a point load. Point load will be a load acting at single point. A load acting at single point is called as point load. Unit of this load can be Newton or it can be kilonewton also. This is SI unit. Let us consider one beam having two supports at A and B. So let reaction at A is RA, reaction at B is RB, and some forces are also acting on this beam. Let this is W1, this is W2, this is W3. So this W1, W2 or W3, these are the various point loads acting on the beam. Let us further move to the second type of load, and second type of load is UDL. This UDL is also known as uniformly distributed load. Let us see the definition of this uniformly distributed load. It is a load spread over some part or entire part of beam. So you can consider the example of a slab. Load of the slab will be acting on the beam, and this load of the slab will be spread over the beam uniformly. So that is called as UDL. The unit of this UDL or UDL can be expressed with the help of these two units, that is Newton per meter, or for the higher amount of loads kilonewton per meter can be used. Now let us see the symbol or the representation of UDL while showing it in the diagrams. So let us consider one beam AB. Let this is point A of the beam, this is point B of the beam. Let us have one reaction RA at this point and reaction RB at point B. Let us show some UDL or over the beam that is acting over some portion of the beam. So you can see that the UDL is acting for length small l. Let us assume that this point is C and this point is D. So UDL is acting between C and D. The length of the UDL is L, while the intensity of UDL is W Newton per meter. Let us assume that length of beam AB is capital L, that is shown over here. It is the distance between end A and end B of the beam. This UDL is sometimes also called as rectangular load, or it is much similar to a rectangular load. So here I am writing over here, it is a rectangular load. Let us see how this rectangular load can be shown in the diagram. Consider one more beam, again AB. Let us assume that it is having two supports at A and at B. So this will be reaction RA and this will be reaction RB. Let us consider that this is point C and point D. In between these 2 points, a rectangular load is acting on the beam. So that is shown over here. So this height of a rectangle is generally mentioned as W Newton per meter. So this is W Newton per meter. Now how to convert how to convert this UDL or rectangular load into point load, that is very important. So conversion of UDL or rectangular load into point load, that is equal to, so point load is equal to intensity of UDL multiplied by length of UDL. So here it is W into small l. This is for UDL. Now again, in this rectangular load, consider that the length of rectangular load is small l, while total length of the beam AB is capital L. Now how to convert this rectangular load into point load once again? So this is for UDL and this is for rectangular load. Point load is equal to, here area of rectangle. Now to find the area of this rectangle, you can see the height of the rectangle is W Newton per meter, while the length of the rectangle is in between CD, it is small l. So area of the rectangle becomes small w into L, that is WL. Here also it becomes WL. So this is point load, or this is the intensity of point load. So in this way we can show UDL into point load. So let us draw a free body diagram of this beam, both the beams AB showing the rectangular load as well as UDL, and let us find out exact location of the UDL. So for the first beam AB having its UDL spread between C and D, let this is CD. I am drawing the diagram once again for understanding purpose. This is L, while this is capital L. This is A, this is B. So for this UDL shown over here, the free body diagram will be like this. This is beam AB having two support reactions. So this is reaction RA, reaction RB. Then this is point C, this is point D. Now we have already seen over here that the intensity of UDL when multiplied by length of UDL gives us the value of the point load. So here this point load can be converted into this UDL can be converted into point load. For that we must know the intensity, so let it is W Newton per meter. Now how to convert this UDL into point load? W multiplied by length of UDL becomes WL, and where it will act, it will exactly acting between the 2 points, that is C and D. So when the UDL is acting between point C and D, then point load obtained from the UDL will act exactly at the center of C and D. So here total length is L. So from C and from D at a distance of L by 2 from both ends, from C and D. So this is WL, and this is the distance at which it will be acting. It will be exactly acting at half distance from C and D. So this is L by 2, this is also L by 2 distance. So you can see here this is L by 2 distance and this is also L by 2 distance, for which the UDL is converted into point load. So always remember, point load of UDL acts at the center of UDL. Then same is the case with rectangular load. Let us consider one beam AB once again. having two supports at both the ends. Let us assume that there is a rectangular load acting between point C and D of this beam. This is C and this is D. So this is small l and this is capital L. Small l is the length of rectangular load while capital L is the length of beam. While the intensity of this rectangular load is given as W Newton per meter. Now sometimes it will be shown like this. So that intensity is nothing but height of the rectangle over here. So free body diagram of this beam will be like this. Draw the beam AB as it is with length L. Then you show the two reactions RA and RB. Mark point C and mark point D on this beam. Now as you know that here we have seen point load of rectangular load is find out by area of that rectangle. So it is again W into L. This is for rectangular load and this is for UDL. So this is how the point load of the UDL is calculated. Intensity into length, and point load of the rectangular load will be area of the rectangle. So here you can see intensity is W while length is L. So L multiplied by W gives us the point load. So let us show that point load over here. Point load obtained from this rectangular load is WL. And where it will act? It will be acting again exactly at the center of the total length, or we can consider that, or we can say that point load obtained from the rectangular load acts at the CG of this rectangle. CG of the rectangle will be at the center of rectangle at the intersection of the diagonals, and which will be at half distance from both points C and D. So this is L by 2 distance, this is also L by 2 distance. So this is how the UDL is converted into point load. Now we are going to start with the third type of load, and that is UVL. It is also called as uniformly varying load. Uniformly varying load. Sometimes it is also called as triangular load. Triangular load. So this is triangular load. Now what is exactly this UVL or triangular load is? Let us first see once again what is UDL. UDL is the load which is spread over some part or entire part of a beam, and its intensity over the specific length remains constant. Like here you can see it is W Newton per meter. That means for each 1 meter length, intensity of the load is W. Here in the rectangular load also, as you can see, load is W Newton per meter, means for each meter length the intensity of the load is W. But that is not the case in case of UVL or uniformly varying load or triangular load. So it is a load whose intensity is linearly varying. So it may decrease or increase. Varying means it may be increasing or decreasing. So a load whose intensity is linearly varying between 2 points. On the beam is called as what? UVL. This is known as UVL. Okay, that means intensity of intensity of load at one point maybe 0, maybe 0, and at other end it may be maximum. So this type of load is called as uniformly varying load or the triangular load. Let us see how we can convert this uniformly varying load or triangular load into point load again. Now this topic is very important. We have now already seen the definition of this UVL or the triangular load. So here now we will see how we can convert this UVL or triangular load into point load. So you have to remember 2 points over here. Two important points are to convert this UVL into point load. We have to calculate area of triangle, area of the triangle, and for location of point load obtained from UVL or triangular load, we have to find centroid of triangle. If you remember these two concepts, it will be very easy for you to convert UVL or triangular load or even trapezoidal load also into point load. So let us discuss different types of triangular loads one by one over here. Consider this triangular load shown in the diagram, which is acting on the beam AB. Let this is your beam AB having one hinge support at point A, and at point B this beam is having a roller support. This is point B of the beam, and let us assume that the triangular load is acting over here on this beam between the 2 points, that is C and D. So this is the triangular load or uniformly varying load. Now how it is uniformly varying load? You can see at this location intensity of the load is 0 and it is linearly varying towards point D. It is increasing towards point D, and at D it becomes maximum. So that's why it is called as uniformly varying load, or because of its shape it is also called as triangular load, as it looks like triangle. So this is the triangular load having intensity W Newton per meter. Now basically this W Newton per meter is the height. It is the height of this triangle, which is W Newton per meter. Let us assume that distance between C and D is L, small l, while the distance between A and B is capital L. Let us draw its free body diagram. So this will be your beam AB. As at point A there is a hinge support, so there will be two reactions. This is AY, this is AX, and here as there is a roller support, there will be only one reaction, so we will call it as RB, or you can call it as BY also. So this is point C. Let the mark those 2 points between which the triangular load is acting. Now as I have told you over here that to convert the UVL or triangular load into point load, you have to calculate area of triangle. So here you can see this is the triangular load. So in this triangular load, base of the triangle is L. Height of the triangle is nothing but intensity of the load. This can be called as intensity. This is intensity. So intensity of load is height, while base of the triangle is length of the length of this UVL, or the distance between point C and point D, and from which we have to calculate the area. So basically we know area of the triangle is half into W into L. So definitely this point load can be converted. This triangular load into point load will be like this. Point load is equal to area of triangle. So that is equal to, what is the area of triangle? Half into base into height. So here 1/2 into base is L, into height is intensity, so W. So this becomes half WL, or we can also call it as WL by 2. So this is how you can convert the triangular load into point load. Now how or where this point load will be acting exactly on this beam? Now definitely we know that it will be acting between C and D, but we don't know exact location of this point load. But I have told you over here that for the location of the point load obtained from the UVL, find the centroid of triangle. Now we know that centroid of any triangle lies at a distance of L by 3 and 2L by 3. So L by 3 from D point and 2L by 3 from C point. We have already seen this. L by 3 distance from the height and 2L by 3 distance from this corner. So this will be the location of the triangular load. WL by 2 is the value of the point load, intensity, magnitude of the point load, and distances. This distance will be 2 times L upon 3. This is 2L by 3, while this is only L by 3. So in this way we can find the exact location of this triangular load. This is one of the type of triangular load from which we can draw the free body diagram like this. Let us discuss one more type of triangular load in the next case. As a next case, second one, consider one beam. Once again, now I will not be showing the different types of support. I will be directly showing you the supports. At A, here there is one reaction, at B there is another reaction, so this is RB. This is RB, and the shape of the triangle is like this. You can observe the difference now. Let this point is C, this point is D. The triangular load is acting between C and D, but you can see the difference here now. In the first case, at C intensity was 0, at D intensity is maximum. So we have got the right angle triangle over here. Here you can see that at C the intensity is 0, at D also the intensity is 0, but in between C and D at the center the intensity of the load is maximum. So this is like isosceles triangle. This is just like isosceles triangle. So we have to consider that this is W Newton per meter. This is nothing but the height. This is nothing but the height of the triangle. And let distance between C and D is small l once again. And as usual, distance between RA and RB will be capital L. So how we can draw free body diagram of this beam from this triangular load? So this is your beam as it is, having two reactions RA and RB. Assume that this is our point C, this is our point D. In between C and D, the point load is going to be act. Now what is the length of triangle? L. what is the height of triangle? W. So what will be the point load conversion? It will be just like this, area of triangle, half into base into height. So again, the point load value will be WL by 2. But exact location of this point load is very important. In this case, as it was the triangular load, right angle triangle, so it was acting at a distance of L by 3 from D and 2L by 3 from C, but it is isosceles triangle. So in this case, load WL by 2 will be acting exactly at half distance from C and D, because CG of isosceles triangle lies exactly at half distance from both corners on the base. So this is L by 2 and this is L by 2. So that is the difference. See, conversion of point load is just similar to the right angle triangle. Here also this triangle is converted into point load by using WL by 2. Here also this triangle is converted into point load using this WL by 2. But here location, from this maximum height, from this D point, the WL by 2 load is acting at L by 3 distance, and from the C it is 2L by 3. While in this case, this WL by 2 load is acting exactly at half distance from C and D. So this is how you have to locate the point load obtained from the triangular load. Let us consider one more type of triangular load. Instead of saying triangular load, we will call it as trapezoidal load now. I will say that this is reaction RA, this is reaction RB. Between A and B there is a point C as well as D. Let the length between C and D is small l. As usual, we are assuming it in all cases. Here, instead of having triangular load, I am going to draw trapezoidal load. So it will be like this. This is a trapezoidal load. So it is very important to know how to convert this trapezoidal load into point load. It is very simple. Assume that at C the intensity is W1 Newton per meter. That means this height is W1, and at D, at this location D, the intensity is W2 Newton per meter. That means this height is W2. Now how to convert this trapezoidal load into point load? So it is neither rectangular load nor it is a triangular load. So we can do one thing here. From this point we can draw one horizontal line, dotted line. Now you can see that this trapezoid is divided into two parts. First, it is a triangle with height W1. Then there is a first there is a rectangle with height W1, and then there is a triangle with height this much. Now this height is to be determined. So definitely that remaining height will be W2 minus W1, because total height is W2, this height is W1, so remaining height will be W2 minus W1. This is W2 minus this is W1. Now we have divided this trapezoidal load into two loads. One is rectangular load and one is the triangular load. Let us draw its free body diagram now. Consider 2 points A and B and having two reactions RA and RB at both ends. As usual, this is C and this is D. It is located. Now we know that as this is a rectangular load, so we can convert this rectangular load into point load directly by using the area of triangle. So height of the triangle is area of the rectangle. So height of the rectangle is W1 and the width is L. So W1 multiplied by L becomes 1 point load, first point load, and it will exactly act at the center of C and D. So at the center I will be having first point load obtained from this rectangle, and its intensity or its magnitude will be W1 into L. Now distance. The distance from C will be L by 2, and the distance from D, it will be again L by 2. I will have one more load that is obtained from this triangular load. Now we also know that how to convert the triangular load into point load. So it is done by finding the area of the triangle. So what is the area of triangle? Base is L, height is W2 minus W1, not entire W2, but for triangle height is only W2 minus W1. W2 is the height of trapezoid, while W2 minus W1 is the height of triangle. So that point load will be half W2 minus W1, this is height, into base is L. So this is the value of point load obtained from triangular load over here. And at what distance it will be acting? At the CG. So we know that CG of the triangle lies at a distance L by 3 from height. So this is L by 3 distance, and so this remaining distance will be 2 times L by 3. So this is how you can convert this trapezoidal load into point load. So you have to do two things over here. First you have to divide that trapezoid into two areas. First is rectangle, second is triangle, and then you have to separately find out point load of the rectangle and separately find out point load of the triangle and locate both on the free body diagram. So this is all about the triangular load. One more type of triangular load is there. You can refer the notes and you can learn that type of triangular load where the shape of the triangle is neither right angle triangle nor it is isosceles, but it will be scalar triangle. But generally that kind of triangle will not be asked in the exam, but it is provided in the notes, you can refer it.